Alright, so in the last section of this chapter, we will discuss some inequalities for martingales and convergence of martingales. So we will begin with a couple of inequalities, and in the first inequality we will use optional stopping theorem for submartingales instead of martingales. So the optional stopping theorem for submartingales, well, it is basically the same statement, except equality becomes an inequality. So if we consider here two stopping times, tau1 and tau2, and we consider some event in the sigma algebra up to the stopping time tau1, then under some integrability condition, the same integrability conditions as in the optional stopping theorem for martingales, when we compute the expectation of x tau2 on the indicator of this event A, instead of equality we get inequality, that this is greater or equal than expectation of x tau1 on this indicator. Okay, of course here I'm assuming that the sequence xn bn is a submartingale. Now the proof would be exactly the same, except in the step where we use the martingale property, we would use submartingale property and get inequality in that step. Okay. Now using this, we will start by proving the following theorem, which is known as Doob's inequality. Right, what this says is that if we have a submartingale sequence, so if xn bn is a submartingale, and then if we consider for a given n a maximum of this sequence up to time n, and then we consider some constant m bigger than 0. In this case, we can control the probability that this yn exceeds this level m by something that looks like Chebyshev's inequality. So it's 1 over m times the expectation of xn on the indicator of this event that we are trying to control, yn greater or equal than m. Now once we prove this, of course, we can also bound this by the expectation of absolute value of xn, or just the positive part, xn plus of xn divided by m. Okay, so if instead of yn we had xn here, this would be just a Chebyshev's inequality. But for submartingale, we can control not just xn, but the maximum of the entire sequence up to n by in the same way as in Chebyshev's inequality. Okay, and the proof will be using the optional stopping theorem. All right, so let's call this event that we would like to control here, let's denote it as an. So this is yn greater or equal than m, or the maximum greater or equal than n. And one thing that we notice here is that this event can be viewed as an event in the sigma algebra of the stopping time tau if we define tau as the first index, or the first time when our sequence crosses this level m. So in other words, this will be the smallest index k. Now here we only consider sequence up to n, so the smallest k up to n, where xk crosses level m. Now of course it's possible that the sequence will not cross up to time n, so we define this k in if such k exists. So if such k exists, and then if not, then we'll simply stop at n. We take tau to be this largest index n. Okay, and clearly this event A is in the sigma algebra because by the time you cross, or at the time when you cross the level m, you know whether maximum up to n is greater or m than not. And if you never cross, that means you actually at time n, and then of course everything, any function of x1, xn is measurable with respect to that sigma algebra Bn. So it's clear that this statement is clear, but of course we can just write down by definition of the sigma algebra B tau, we want A intersected with tau less than or equal than k to be in Bk. And here we only consider indices up to n, so I'm going to assume that this k is less than or equal than n. And of course then we can simply rewrite this intersection as the fact that the maximum up to time k of our sequence xi exceeds m. Right, so it's clearly the same thing, and this is expressed in terms of x1, xk, so this is in Bk. So by definition, we get exactly what we want, right? That this means that the event A is in the sigma algebra up to the stopping time. And then we are going to apply optional stopping theorem to the following two stopping times. So the stopping times will be tau, and the second stopping time will be just the last index n. So in this case, tau is less than or equal than n. And so the optional stopping time then tells us that the expectation of xn on this event is greater or equal than the expectation of x tau on this event. And finally, it just remains to notice that on the event A, when our sequence crosses m before time n, the value of the martingale at the stopping time tau will be greater or equal than m, right? So the sequence crossed m, and at the first time that happens, x tau will be greater or equal than m, so we can bound this from below by m times the expectation of the indicator, which is just the probability of A. And if you take a look, that's exactly the inequality that we wanted, right? That the probability of this event A, where the maximum crosses m, is bounded by 1 over m times the expectation of xn exactly on the indicator of this event. And so this finishes the proof of this inequality. Right, so let's look at one example of application here. Let's look at the so-called second Kolmogorov's inequality. So maybe to motivate this inequality, let's first recall Chebyshev's inequality for the sum of independent or maybe uncorrelated random variables. Right? So when we consider a sequence of random variables xi, let's say they are already centered, so we don't need to subtract the expectation. And then we'll consider their sum Sn. Okay, so one way we use Chebyshev's inequality when these random variables have finite variance is to write that the probability that the sum Sn exceeds some positive level m, you square both sides and then apply Chebyshev's inequality to get 1 over m squared times the expectation of the sum squared. Okay, and in the case where the expectation of xi, xj for I not equal to j is 0, so your random variables are uncorrelated, or for example when they are independent, the expectation of Sn squared is just the sum of expectations of xi squareds. So this was Chebyshev's inequality for uncorrelated random variables. Now here we will obtain something a little bit stronger under also a little bit stronger assumption. Namely, let's suppose that the expectation of random variable xj plus 1 conditionally on the sequence up to time j is 0. Okay, for example, again, if this sequence xi are independent random variables, you will have this as a consequence of the assumption that they are centered. Now, in this case, we see that the sum will be a martingale, so Sn Bn will be a martingale, where, as usual, by default, we assume that the sigma algebra is just generated by the sequence itself. And in this case, we'll be able to control not just the last sum Sn, but the maximum of partial sums Sk for k from 1 to n. Right? The probability that the maximum of partial sum exceeds m will be controlled by the same inequality as above. Okay, because first of all, we can again square both sides. And then we notice that by conditional Jensen's inequality, Sn squared will be submartingale, right? So after squaring, this martingale becomes submartingale, and so we can apply the Doob's inequality above to bound this by 1 over m squared times the expectation of Sn squared. Okay, just like above. And of course, this assumption that the expectation of xj plus y is 0 conditionally on the sequence up to time j will also give us that they are uncorrelated. So this will again be the sum of their variances, or expectation squared. Okay, so under slightly more restrictive assumption, we get a much stronger control of partial sums along the entire sequence rather than the final sum here. All right, and for further consequences of this Doob's inequality, please take a look at the exercises. Now, the next inequality that we'll prove, that it will be used in proving the convergence of martingales or submartingales, and this is the so-called Doob's upcrossing inequality. Okay, and before we state this inequality, let's try to motivate this by thinking about convergence of sequence xn. So when we'll deal with convergence of martingales or submartingales, we can look at the event when the limit of this sequence, let's say as n goes to plus infinity, but when n goes to minus infinity, one can just write something similar. So when this limit exists, let's actually instead look at the complement. That what does it mean that this limit does not exist? Okay. Well, one way to write this is to say that the lim sup and lim inf are not equal, right? Particularly lim sup will be strictly greater than lim inf. Now, when lim sup is strictly greater than lim inf, we can insert a pair of rational numbers in between the two. So we can write this event as a union over all a and b not equal, and a and b rational numbers of the event that the lim inf is less than or equal than a, plus less than b, less than or equal than lim sup. And if you look at one of these events for a fixed a and b, right, so if we want to show that the limit does not exist with positive probability, we have to show that one of these events has positive probability for a fixed A and B, or the other way around, if all of these probabilities are 0, then the limit exists with probability 1. So we can fix a pair of rational numbers A and B, and then basically if we consider these two levels A and B, the fact that the lim_inf is strictly less than lim_sup means that your sequence will oscillate between these two levels, right? So at some point you have to keep crossing below A, and then at some point you have to go above B. And it has to happen infinitely many times. So you must have this kind of oscillation infinitely many times if this event occurs. Okay, and if we show that you cannot oscillate between two levels infinitely many times, well, that will imply that the limit exists with probability 1. Okay, and so this motivates the following definition. So these times when you cross A and B, right, we'll denote them. This will be stopping times, and the first time you go below A, we'll call it tau 1. Then the first time you go after that above B will be tau 2. And then this will be tau 3, tau 4, and so on. Okay, so in other words, we'll consider the following stopping times. So tau 1 will be the first time when your sequence xk goes below A. Tau 2 will be the first time after the stopping time tau 1 when your sequence goes above B, and so on. So your odd indexed stopping times will be the first time after the previous stopping time when you cross below A, and the even indexed stopping times will be the first time after the previous stopping time when you go above B. And we are going to count how many times this happens. And so as a result, we'll consider the following definition. Okay, we'll be interested in the number of these up crossings from the level A to B. Okay, so this will be called the number of up crossings of this interval AB, and it will simply be, so the notation we'll use will be nu ABN, and we'll count how many times this up crossing happened up to time n. So this will be, in other words, this will be the largest index k such that tau 2k is less than or equal than n. Okay, so we'll look at pairs of these stopping times, and we'll count how many times you went from below A to above B. And so oscillation means that this number will be infinite or will go to infinity when n goes to infinity. And if we want to prove convergence, we want to control this number and show that it does not go to infinity. Okay, and this will be accomplished by this Doob's upcrossing inequality. So our next theorem will be the following result. In the above notation, it will say that the expectation of this number of upcrossings will be less than or equal than expectation of xn minus a, the positive part of this difference, divided by b minus a. Okay, and the assumption here is the same as above, that our sequence xkbk is a submartingale. All right, so to prove this result, first of all, let's notice that we can simplify slightly if we just redefine our submartingale. So let's consider this function x minus a, the positive part. Okay, and then this is a non-decreasing and convex function, which implies that your submartingale, when you plug it into this function, will still be a submartingale. Okay, this is just by conditional Jensen's inequality. And so we can simply redefine this to be our new submartingale. So, you can redefine this to be xn, or maybe for a second, let's say we redefine this to be zn, and then we can notice that every time x goes below a, this zn that's when zn hits 0. And every time x goes above b, this zn goes above b minus a. So the number of upcrossings for the original sequence x of the interval ab, it's the same as number of upcrossings of this transformation of the interval 0 b minus a. Okay, and so just to keep the notation simple, let's just, instead of using this new notation, let's just for simplicity assume that our original martingale was already non-negative, so you can only hit 0. So original sub-martingale is non-negative, then you consider some positive b, and what we want to prove is this inequality that the expected number of upcrossings of the interval 0b up to time n is less than or equal than expectation of xn over b. Okay, so just to simplify, just assume that that transformation was already applied and we are in this setting. Okay, and the way this proof goes is it's very clever. Basically, when we are on our way up, crossing from A to B, right, we'll just consider these indicators that a time j is exactly in between these two consecutive stopping times. So let's consider this indicator, let's call it eta j, that our j is after some odd index stopping time. So j is strictly bigger than tau 2k minus 1 and less than or equal than tau 2k for some k. In other words, we have already crossed the level A earlier, and now we are on our way up, but before we cross level B next time. And what we notice here is that this event, so if you fixed any specific value k, then this event, it's b j minus 1 measurable. Okay, and well, to check this, you just rewrite this event, right, as the first inequality. You can write this as less than or equal than j minus 1, and the second inequality, you can instead look at the complement, and the complement is that the next stopping time is less than or equal j minus 1 again, right? And both of these, by definition of stopping time, are b j minus y measurable. So in other words, at time j minus 1, you already know that your next time will be on the way up or not. And that's, of course, because we chose these inequalities to be, the first one is strict and the second one is not strict. Okay, and then once we notice this, the main idea here is simply count the steps we take on the way up. So in other words, we are going to sum over all j from 2 to n, because at time 1 we cannot yet be on the way up. We have to first cross a. So we can start summing from 2 here, indicator that we are on the way up, and then increment what's the size of the step we take between time j minus 1 and j. And because you count your increments only on the way up, every time you cross from a to b, these steps will add up to something at least of size b. And sorry, here a is equal to 0, so every time you add up these steps along one up crossing, you will get b. So this sum will be greater or equal than b times the number of up crossings of interval 0b up to time n. Okay, so that's kind of the main idea, and now we just have to take expectation and use the properties of the sigma algebras and sub-martingales. Okay, so if you take expectation, you get this inequality here. At the next step, we will first take conditional expectation given j minus 1 or sigma algebra up to time j minus 1. And then when you take conditional expectation given sigma algebra up to time j minus 1, well, first we'll use what we just said about that this indicator eta j will be already measurable with respect to that sigma algebra, so we can treat it as a constant. Then we take expectation of xj given that sigma algebra, and the last term is also measurable, so we treat it as a constant on bj minus 1. So this conditional expectation here only is applied to xj. Okay. And now we use the fact that this is a sub-martingale, so this increment here is non-negative, right, because this is a sub-martingale. Okay, because this difference is non-negative, when you multiply it by this indicator here, right, it only gets smaller compared to the same difference without the indicator. So in other words, if we drop the indicator, we will just increase. And so that's exactly the place where we used the fact that this difference is non-negative. If it could be negative, then dropping the indicator could actually decrease the difference. Okay, but here, because of this sub-martingale property, we can write this upper bound without this indicator. Okay, and then again can be written just as a sum of the expectations of xj minus expectation of xj minus 1. And so you get expectation of xn minus expectation of x1. And because our submartingale is non-negative, well, in this case, if I just drop x1, we get again less than or equal than expectation of xn. And that's exactly the inequality that we wanted to prove. So this finishes the proof of this Doob's up crossing inequality.